In the previous video we looked at the rational function f of x equals 1 over x plus 2, and I discussed in general what rational functions are like, how they behave. We looked at a break or discontinuity in this function. That's where the denominator is equal to 0, where x plus 2 is equal to 0. In other words, x equals minus 2. The graph has two sections. One section is in the shape of a hyperbola, actually, and the other section is the image of this section under central symmetry in this point here. That's where the vertical asymptote crosses this horizontal asymptote. The horizontal asymptote is actually the x-axis. So the asymptotes are lines that the graph approaches but never crosses. So we put arrows on the sections of the graph to indicate parts of the graph that extend that never actually cross the asymptotes. Now in this question, in part 3, we have this new function, g of x equals x plus 2, and we want to draw the graph of it. Now this function is a line. Its graph is a line, a straight line, because power of x is 1. It's got the form ax plus b. A function that has this form is linear, which means its graph is a straight line. So a and b are just any numbers. In this case a is 1, b is 2, but a and b are any constants. In order to draw a line, a straight line, all we need to do is pick 2 points on the line. And the domain we're allowed to choose for x values runs from -5 to +1. So x lies between -5 and +1. So we can pick any value of x in that domain. So a convenient value of x to pick is 0. So if we calculate g of 0, we plug 0 in for x, so we have 0 plus 2 equals 2. So when x is 0, the y value is g of 0, which is 2. So 0, 2 is a point on the line. So let's just show that point. 0, 2 is this point here. So when x is 0, y is 2, or g of x or f of x, whatever the function we're talking about, g of x here. Now we can pick any other value for x. We could let x equal 1, for example. Actually, I'm going to choose x equals -4. So we just plug -4 in here. We have -4 plus 2 is -2. So when x is -4, y is -2. So we have the point -4 minus 2, which is here. So here's g of x, and f of x is our rational function. So 2 points is all that's needed. You could work out more, but there's no need to, since it's a line. All those points will lie on this line. In part 4, we want to use the graph to estimate the range of values of x for which f of x is less than or equal to g of x. Well, let's first of all see where f of x equals g of x. Okay, we want a range of values of x for which f of x is less than or equal to it, so we'll do the equaling bit first. Where are the functions equal? Well, that's where the line crosses the curve. So this is one point, and this is another point. So for this point here, f of x will equal g of x. You can actually see from the graph that it's -3. F of -3 should equal g of -3. And you can see from the graph that f of -1 should equal g of -1. Actually, f of -1 is 1. And g of -1 is also 1. So they're both equal to each other. F of -3 is -1, and g of -3 is -1. You can see from the table, f of -3 is -1. And if you calculate g of -3, we just plug -3 in here. We get -3 plus 2 is -1. So you can see it from the graph. If you've drawn the graph any bit decently. How would we solve this without the graph? Well, we just write the two functions equal to each other. So we write f of x, which is 1 over x plus 2, equal to x plus 2. And we solve this equation here. Try to find the values of x that make both of these equal. And we should get minus 3 and minus 1 for our answers. So how do we solve this equation? Well, anytime you see a fraction in an equation, you try to get rid of the denominator. How do you get rid of this denominator? Well, you multiply both sides by this denominator. So you multiply the left by x plus 2, put x plus 2 in brackets. But you must then multiply the right by x plus 2 to balance both sides. That's how we get rid of a denominator and get it all into a straight line. So when we multiply out the left, these cancel. So we just get 1 over 1, which is 1. And if we multiply the right hand side, x plus 2 is multiplied by this. There are two terms here, by the way, so we bracket this. All of this is multiplied by this. X plus 2 times x plus 2 can be written more succinctly as x plus 2 squared. X plus 2 times itself. Now how do we solve this? Now, the hard way to solve it would be to expand this out to get x squared plus 4x plus 4 equals 1. Then bring the 1 over, so we'd have x squared plus 4x plus 3 equals 0. We'd have a quadratic equation. We could factorize it or use the minus b formula to solve it. You know, but that's too long. A much quicker way is simply to get the square root of both sides. So we just get the square root of both sides, because if we get the square root of something squared, we just get that something. We get x plus 2. So whatever x plus 2 is, it has to be the square root of the right hand side. The square root of 1, however, can be either plus 1 or minus 1. Two answers. Because plus 1 squared is plus 1, but minus 1 squared is also plus 1. So what have we got here? We have x plus 2 can equal plus 1, or x plus 2 can equal minus 1. Let's say x plus 2 equals plus 1. Well, that leads us to x equals plus 1 minus 2, which is minus 1. So x equals minus 1 is a solution. So you can see that's what we saw earlier from the graph. And we can also put x plus 2 equal to minus 1 to give a second equation, leading to x equals minus 1 minus 2 or minus 3. So x equals minus 3 is the other solution. So to summarize, we have that f of minus 3 equals g of minus 3. And actually, if we want to work that out, that answer is minus 1. And the other value of x we got was minus 1. In other words, f of minus 1 equals g of minus 1. And if we work that out, we actually get 1. But that's not important. This is just summarizing what we did. Now let's get back to answering the question. We want to find out where is f of x less than or equal to g of x. So f of x is the brown function, and the g of x is the blue function. So where's the brown section underneath the blue section, basically? So this here, this section of f of x is less than or equal to g of x. Okay, so all you do is look to see where f of x is below the line, that's all. So there's two sections. Actually, I'll do those two sections in a different color. I'll do them in green. So this section here and this section here of f of x is less than or equal to g of x. So for what values of x correspond to these two green sections? Well, you can see that it's values of x that are greater than or equal to minus 3. But excluding this point, we have to circle this out. Because at this point, the function is undefined. It could either be up to plus infinity or minus infinity. So if x is greater than or equal to minus 3, if with this point accepted, say it's this point here, we find that f of x will be less than g of x. Or if it's this point here, if we calculate f of x, we get this distance, which again is a lot less than g of x. Or over here, if we take this point and calculate f of x, we're down here, whereas g of x is up here. You can see that f of x is below g of x, f of x is less than g of x. So here's the answer to part 5. X is greater than or equal to minus 3. It could equal minus 3 because at minus 3, f of x equals g of x, that's allowed. But we have to leave out this point. So it's all the values greater than or equal to minus 3 with this point taken out. So you can just circle that to indicate that that point has been removed. It turns out that this point was not necessary. You know, it doesn't come into the calculation. It's this point here that comes into the calculation. In part 5, we have to prove that this curve has no turning points. Now, a turning point on a curve would be a local max or local min. Like if our function looks like this would be a local max. And the tangent to the curve at this point is a horizontal line. Its slope is 0. But the slope is also the derivative of the function. Say the function is here, is the derivative of the function. dy dx worked out at this point here, whatever this point is. The derivative will be 0. So that's a turning point. That's an example of a turning point. That's this particular turning point is a local maximum, but we could also have a local minimum. The tangent to this point is also a horizontal line. Its slope is 0, and the derivative at this value of x will be 0. Now, if we look at f of x, the tangent to f of x is never horizontal. No matter what point we take on f of x, on the graph of f of x, the tangent will never be a horizontal line. Like if we take this point here and draw a tangent in, that's not a horizontal line. Or this point here is not horizontal either. No matter where we go, even this point here, if we take the tangent, it's not horizontal. It's nearly horizontal, but it's not horizontal. The tangents are approaching a horizontal line as x goes off to plus infinity, or as x goes off to minus infinity. If we take a very large negative number and get the tangent, it's approaching a horizontal line, but it never becomes horizontal. Only as x gets to minus infinity, or x gets to plus infinity. And all the points around here are far from horizontal. If we take the tangent here, see it's a very large negative slope. Or actually the tangents always have negative slope. Take this point here, it's negative slope, sloping downwards. All the tangents have negative slope, as a matter of fact. And it's only when we take a very large value of x does the tangent approach a horizontal line, but never makes it, because the curve is always decreasing but never reaches the x-axis. Similarly here, the curve is approaching the x-axis but never becomes horizontal. So you can see from the graph, that's one way to prove it. How would we prove it more mathematically? Well, we note that dy dx equals 0 at a turning point. So what we could do is find the turning points by putting dy dx equal to 0. That's how you find the turning points of a function. You put the derivative equal to 0 and solve for x. That gives you the x values at the turning points, these values, on the x-axis. So let's look at our function. So there are two ways we could do this. We want to get dy dx and set it equal to 0, so this is a quotient or fraction. We could use the quotient rule, so u equals 1, v equals the denominator, which is x plus 2. We calculate du dx, the derivative of 1 with respect to 0, with respect to x is 0, it's just a constant. dv dx, differentiate 1x with respect to x, we get 1. Differentiate 2, we get 0. And then use the quotient rule. dy dx equals v du dx. And we plug everything into this, so we have v is x plus 2 times du dx, which is 0, minus u, which is 1, times dv dx, which is 1. So we multiply v by du dx and subtract u times dv dx. And we divide all of that by v squared. That's x plus 2 squared. So this gives us x plus 2 by 0. Well, that just gives us 0. Then we minus 1 by 1 is minus 1. So we end up with minus 1 over x plus 2 all squared. To find turning points, we'd have to put this equal to 0. We put the derivative equal to 0 because the slope of the tangent is the derivative. The derivative of a function is the slope of a tangent to it. So we put this equal to 0 and then we'd solve. But the problem is we cannot solve this thing because we have a fraction. This is a fraction equals 0. The only way a fraction can equal 0 is if the numerator, that's the thing on top, equals 0. And it doesn't in this case. We only have to look at the numerator. And it's not 0. So we cannot solve. In other words, there's no value of x that we can put in here that'll make all of this thing 0. As a matter of fact, this thing here is always negative. Okay, the tangents always have negative slopes, as I pointed out to you. For any point on the curve, the tangents are sloping downwards like this. That means negative. Slopes are less than 0. Why is that? Well, we have a fraction here. The number on top is negative. -1 is clearly negative. But look at the denominator. It's something squared. If you take anything and square it, it's always positive. It doesn't matter what x is. X could be -1,000,000. -1,000,000 plus 2, whatever that is. But if we square it, it'll be something positive. If you take a negative number and divide by a positive number, you get a negative number. So the slopes of the tangents are always negative. They're never 0. Unless you let x go off to infinity. If you let x go off to infinity, of course, we'll have -1 over infinity, which is 0, but that doesn't count. X equals infinity is not a solution. X equals infinity would correspond to what I said earlier. If we take a very large value of x, an infinitely large value of x, we'll have a tangent to the curve that's almost horizontal.